Fire away! Ground launch projectiles. Fire! Okay, what is a projectile? An object that is launched into the air with some initial velocity. Okay, it can be launched at any angle. And it's in free fall after the launch. There's no outside forces acting on it except the force due to gravity. So when we fired our rockets up into the air, they were vertically launched projectiles. But we could have launched them at some angle. So here's a soccer player getting ready to launch a soccer ball at some initial velocity at an angle of 30 degrees above the horizontal. So if it's fired at 12 meters per second, we can calculate the components of that vector using our knowledge of vectors. The horizontal part of the ball's velocity is the initial velocity times the cosine of the angle. Vix, in this case, 10.4 meters per second. We can calculate the the vertical component by using sine. Vi sine theta gives us the vertical component of that velocity, in this case, 6 meters per second. So, what do we know and what can we do when we figure out these problems? We can figure out the time of flight, how long it's in the air. Remember, the time to the top is equal to half of the time of the flight, just like we did in our rocket lab. The vertical distance, we can figure out how high a projectile will go, the time to the apex, maximum height, and we can figure out the horizontal distance, how far it will travel along the ground, and in that we call that term range. What's the range of the projectile? So, what assumptions do we need to make about the vertical component? In this case, the initial vertical velocity we know, VIY. The acceleration due to gravity is going to be negative 9.81 meters per second squared towards the Earth. We know that the final velocity at the apex is 0. For a brief moment in time, it reaches 0 at the top of its flight. And we know the time to the top is equal to half the total time. Time up equals time down. For the horizontal part, well, we know that the initial velocity in the x can be calculated. The acceleration in the x is always 0. You have no acceleration in the x direction. The horizontal velocity is going to stay constant, therefore. It's not going to change. So let's look at a projectile vector diagram to see the projectile vectors. So here's that same soccer ball being launched at 12 meters per second at 30 degrees above the horizontal. You'll notice that it describes the parabolic path. It reaches some apex in the middle of its flight and then comes back down to the Earth. Well, if we look at the vector components, we can actually see how this path is created. Okay, there's the launch velocity at the angle. Okay, it can be broken up into its components, horizontal and vertical. Notice that the horizontal component, because there's no acceleration in the x, never changes. So you'll see it the same everywhere along the path. The vertical component, however, has to experience a negative acceleration of 9.81 meters per second squared towards the Earth. So as the object is reaching the apex, notice that the velocity vectors get smaller until it reaches the top when it's at 0. On the way down, they begin to grow and get faster and faster towards the Earth. And it's the vector sum of those two vectors which give us that parabolic path. Can you see how the sum of those two vectors is going to give us that parabolic path? That's why we have those parabolic flights, and that's all there is to ground launch projectiles. It's simply keeping track of both horizontal and vertical components of an object moving now in 2 dimensions. Okay? VI Fy equals VIY, negative VIY. That's just a little trick there you learn at the end. Okay, gang, well, that's it for ground launch projectiles. We'll move on next to horizontally launched projectiles.